Hi, everybody. I'd love to introduce Nicholas Muller from CMU, who's been working on the connection between the economics of the global economy and climate change and pollution to understand kind of the interaction between these two, the natural world and the economic world. Welcome, Nick.
Thank you very much, Greg. It's a pleasure to be here. As you mentioned, I'm going to talk today about some of the modeling issues and implications of those modeling issues for air pollution with a bit of greenhouse gases and the implications of that measurement for both firm and economy-wide estimates of value. Thanks so much. And please feel free to interrupt if there are questions. Okay, so today I want to talk about two applications of measuring environmental pollution costs. One, I want to think about environmental accounting, which is an old area of research in economics that recently got a significant connection to current government action in the Biden administration. And the basic premise of this area is that standard metrics like gross domestic product or gross national product are incomplete, and they omit critical contributors to social welfare like ecosystem services, pollution damages, and the value of natural resources in situ. I'll talk about an application to the US economy and to global context in our time together today. The second is thinking about firm value and performance, and this really pertains to say, within the last 5 years, push to include environmental, social, and governance criteria in the management of financial assets. And the research here is based on the premise that much of the products and metrics that are offered in the financial services industry are really not connected to science. And so I'll talk about how I make that connection in my research, and we'll talk about an application to the S&P 500. But before we jump into all that, I want to talk a little bit about where I'm headed today, and then we'll have a couple slides on the motivation for the topic. So that's coming with an example of the historic look at the US economy cleaning up and repercussions for our measurement of growth. I'll talk about how it is, just very briefly, conceptually, that we measure economic activity and performance. I'll talk for a fair bit of time and at some depth on the empirical modeling methods, if that's of interest to folks, and then move on to research or results, rather, in terms of economy-wide, sector level, industry level, and firm level statistics, and then I'll conclude. So empirical observation, just gathered data or photographic evidence, tells us that in the 20th century, pollution in the US has fallen precipitously. This is a picture of Pittsburgh, where I'm sitting now, from the 1940s during the day, and you can see significant smoke levels from both local economic activity like steel manufacturing and also home heating with coal. This is a picture from the 1970s in Pittsburgh. You can see significant smog still remaining, and then this is a picture from Pittsburgh today, right? So just casual empiricism that tells us that air pollution levels have changed a lot. If we take a step in the direction of scientific rigor, this is an excerpt from a really interesting paper in the Proceedings of the National Academy of Science that used bird specimens from museums in the US that had been gathered over the course of the late 19th and the rest of the 20th century. And electron microscopy was used to count the particles of atmospheric black carbon that had stuck to the birds over the course of about 135 years as a means to try to count air pollution when it had not been monitored. The graph on the left-hand side is just a statistical representation of the intertemporal distribution of this air pollution measure. And you can see not only has that measure dropped in trend over time, but you have really clear elicitations of business cycles, including the Great Depression, that big trough in the middle of the time series when the US economy basically shut down. And then as the economy came out of the Great Depression in the World War II era, you can see a big uptick. And then in the post-1960 era, the environmental regulatory era, you see the trend falling down, right? So this is just another way of saying there's both photographic and scientific proof that pollution levels have fallen a lot in the US economy. So what I do is I convert measures, physical measures of environmental pollution into dollars, and then integrate those dollars into measures of economic output or firm value. This graph is showing you using empirical data gathered by state regulatory agencies and ultimately the US EPA. When we monetize air pollution damage over the last 60 years in the US, air pollution went from contributing a stunningly large share of, or a stunningly large fraction of GDP, over 30% in the pre-regulatory area, down to under 10%. We're currently around 5% in the US. So this is just, again, another way of saying, look, not only have levels changed, but when we monetize this stuff, the burden relative to economic output that pollution imposes on society has fallen a lot. So what does this mean? Well, when I think about measuring progress for society or an economy, I don't really think about GDP in levels. I think about GDP in growth. And the measures that we just looked at have significant implications for growth if we integrate those pollution costs into what I refer to as an adjusted measure of economic output. So take GDP and subtract off these essentially health and productivity costs that are associated with air pollution. If we compute growth in those two things in two eras, we get a very interesting reversal right around 1970. So on the left-hand side of the screen, when pollution levels and damages were rising, GDP was growing at over 2.5% per year on a real basis. And the adjusted measure of output, where you deduct off air pollution costs, was growing less than that, because what was happening was this burden from air pollution was rising relative to GDP. After the onset of environmental regulations in 1970, you can see this orientation flips, where GDP growth starts to fall. This is a well-known productivity lapse that's been studied in the economics literature. But if we deduct off air pollution damage, it's actually growing more rapidly than GDP over this time period. In some recent research for the Brookings Institute, this is a very similar graph. It's now looking at productivity growth. So this is GDP per hour worked, the adjusted measure, EAP per hour worked, and the gray bar is air pollution damage per hour worked. And you can just see how this reversal is a function of whether or not air pollution damages are growing relative to GDP, or if they're falling or growing less than GDP. And that gives us this reversal in the relative rates of growth in the environmentally adjusted measure versus the market measure.
Question: is there
Sure.
this where, if the economy is perfectly clean, then the drop in pollution can contribute to this? Is that right?
Yeah, if it's perfectly clean and you're literally talking about zeros, then you're deducting off zero and you're just replicating your GDP measure. If air pollution or environmental pollution costs are growing at the exact same rate as GDP, there's no difference in the adjusted measure or GDP, right? So there's two points at which you get the exact same answer. I'll talk a little bit about developing countries later in the talk. It's really interesting, both empirical experiment and thought experiment, to think about China and India and some of the other economies that are at more like the pre-regulatory period in the US, and the implications of that for both supply chains and economic growth more broadly.
Interesting.
So not surprisingly, sectoral and firm level contributions to damages are not equal. This is a more recent paper of mine, co-authored with a graduate student at Carnegie Mellon and a colleague at Stanford. And it's showing you by sector how contributions to air pollution damages have changed. The one that's really striking here is utilities. Damages from utilities have plummeted as the contribution of coal-fired power to overall economic output in electric power generation has fallen. Agriculture is a stubborn contributor to air pollution damages, coming from a variety of sources within that sector. And then the other one is all the way on the right-hand side of that graph is all others. And what's in all others that's really become important are wildfires. Um, I'll show some empirical results on air quality for wildfires a little bit later, but just recognize that the total damages there are now rivaling manufacturing and utilities combined, which is tells us that managing air pollution from wildfires, this is separate from managing fatality risk from fires or property loss, is a really, really big policy priority. And then finally, in terms of specificity, what I've done here is drilled all the way down to the firm level. And I'm showing you 4 different companies that are in the S&P 500 in the utility sector. American Waterworks, which basically moves irrigated water around the West. Xcel, big power producer, Edison International, and NRG. And what I do is I take the damages that are attributable to facilities owned by these companies, divide through by the number of shares, and then deduct that per share damage from the reported share price in our financial data. And you can see for a company like American Waterworks, it doesn't really make that big of a difference. They don't produce a lot of pollution. Xcel and Edison International, you see a significant correction of sorts. When you look at NRG, that over the time series that this graph covered, owned a lot of coal-fired power generation capacity. Poor NRG, when you correct for air pollution damages, appears to have a negative share price, which means the value added for this company as measured in financial markets is less than the air pollution damage coming from the facilities that this company uses to produce power. That notion of damages larger than conventional measures of value is not new to this research. We published a paper some 13 years ago, which I'll just touch on briefly later in the talk, that noted greater air pollution and CO2 damages from a whole host of industries in the US, which made us a bunch of enemies in the public relations sphere, but was then replicated by others using like modeling techniques. So
I read this value as this would be the value of the company if this pollution was fully charged to the polluter.
Right. Yes.
Got it.
So if either markets or a regulatory body that taxed emissions precisely at their marginal impact, and then we deducted that liability from the firm's output level, in the case of financial markets, from expected profits, that's correct. That's what we would get, which just tells me over and over again that coal, unabated coal, is not a good way to make power.
Right.
Okay, so I want to talk, as I said, very briefly about how economists measure economic performance broadly, how that links to the work I'll be talking about today. So that comes next, and then we'll talk about methods and results. So going way back in history, in the 1930s, during the Great Depression, countries really had no systematic way to measure national output and unemployment, our sort of standard macroeconomic aggregates. This frustrated the FDR administration during that epic downturn in their efforts to design policies to manage the Depression. As a result, the Department of Commerce hired Nobel Prize-winning economist Simon Kuznets and his team to design a system of national accounts, and the rest is history. He produced the first estimates in the 1930s, and this became a formalized part of economic statistics in the 1940s. So depending on your view, GDP was either an heroic achievement or it totally mismeasures economic welfare. And just for the clarity for our attendees, I tend to fall kind of in the middle. I think we're better off having it, but I think it can be improved. So how are these accounts, GDP, GNP, and like statistics, how are they incomplete? They're incomplete in that they don't capture what I'm talking about today, which are costs in terms of illness and productivity from pollution damages. They don't measure the value of home production. They don't measure the value of leisure time if that's not used through recreation and tourism in markets. And they don't value natural resources unless they're used and consumed. These deficiencies, these areas where the accounts are incomplete, are especially important, in particular for the pollution side of things, in two contexts. When evaluating policies or measuring the value of industries with impacts that lie outside the market boundary, we'll talk about what that means with some pictures in a minute, and in periods of intense technological change. This latter one, the example I often use with my students is when we transition from flip phones to smartphones, right? They're still tracked as phones in the national accounts, but clearly the value and the bundle of services that are provided by those technologies are not the same. And so as prices change, we really need to think about prices per unit service rather than just prices. So in 2018, the Nobel Prize in Economics was split between Bill Nordhaus and Romer, specifically for their work on points 1 and 2. And that's just recognition that in the recent economics literature, the importance of these issues is recognized by the Nobel Committee. So what are industries that have impacts outside the market boundary? Well, it's a real photograph, but it's kind of a caricature, right? This is steel production back in the early 1900s, late 1800s in Pittsburgh. And it's my contention, based on later research, that all that smoke and particulate matter coming out of the stacks that's not valued by markets, that's not affecting firm value, actually has an impact on social welfare, and we should be measuring it. And if we're talking about impacts that look this extreme, we are probably not doing a good job of measuring the value of this industry and manufacturing broadly and GDP broadly. So here's another picture, same setting. And times of technological change, I talked about smartphones. We're obviously living in a time of profound technological change. These are just two examples. Our transition to renewable power generation, what the bundle of services that wind and solar provide in addition to just power, how their costs have changed over time. All of this is not going to be well captured in an index of economic performance that treats power as power. Okay, so a little bit more on GDP accounting. GDP is comprised of consumption, investment, government expenditures, and net exports. And the way we compute GDP, and this part's actually important for my research, is it's a price times quantity metric. So the number of goods produced times their market price. When I total up air pollution and greenhouse gas pollution damages, and I then work towards building those into an adjusted measure of national output, I try to mimic the way in which GDP is calculated, in the sense that it's the marginal value of a unit times the number of units produced, rather than something like the area under a demand curve for the microeconomists in attendance. And so when I think about that, what my co-authors and I came up with was this notion called gross external damage. And that's the number of tons of a particular pollutant produced times the marginal damage that those particular tons produce. And so it's like a shadow price or a pseudo price for the emission times the reported emissions from a particular pollutant emitted by a facility, to just analogously approach the problem of aggregate value estimation in the way that's done in the conventional accounts. And so that begs the question, how do we build this GED metric into a measure like GDP to deduct off these costs? And so the literature provides some guidance, and it tells us to deduct GED from GDP, or if we're looking at sectors and industries, from value added, since value added adds up in total to GDP. Or if we're looking at market capitalization or some measure of the value of a firm, we're deducting the GED for the firm, likewise off that aggregate measure of value. So When I report EVA, or when I talk about EVA later in my presentation, you'll know that EVA is just this adjusted measure, environmentally adjusted value added. And EAP is just environmentally adjusted productivity. So that's our standard productivity measure, GDP divided by hours worked. This is just deducting off the numerator pollution damage, and that gives us that net measure per hour worked. Okay, so on to the how do we estimate these damages part of the talk. My dissertation research, which was conducted under Rob Mendelsohn and the Nobel Prize winner Bill Nordhaus at Yale some years ago, those two gentlemen have developed what are called integrated assessment models for, in their case, the measurement of damages from long-lived greenhouse gases. And I adapted that approach to the case of air pollution, which is what I'll talk most about in terms of methods. The research that we'll look at in the results section combines greenhouse gases and air pollution. The basic idea with these models is that we're integrating findings, insights from multiple scientific disciplines, not just economics, to try to emulate how economic activity results in pollution emissions, so physical residuals from productive economic activity. And the goal then is to emulate how those pollution emissions behave in the natural environment, whether it's in the air and deposition like particulate matter, or in the air and the subsequent migration to the stratosphere, if we're talking about greenhouse gases, or being discharged into a waterway and how the physical flows result in dispersion. That's the goal, and I'll talk a bit about that phase and how the modeling that we use works. We then, because we're not just interested in like counting tons and counting concentrations, we need to know who or what is exposed to this stuff. So, for instance, how many people are inhaling how much particulate matter in a given period of time. That's exposure. Because susceptibility to exposure varies over the life cycle, it varies by income, it varies by race and gender. We have what's called dose response functions that translate physical exposure into impacts like cases of asthma and emergency room visits, et cetera. And ultimately, what we focus on most is the elevation of mortality risk, that is, the chance of dying that's associated with inhalation or ingestion, if we're talking about water pollution, of many of these pollutants. And then finally, since, as I said at the beginning of my talk, since I'm generally interested in, and the economics discipline is generally interested in taking these exposures and impacts and mapping those into a measure of value, whether it's firm, industry, sector, or economy, we need to monetize. And so that's the valuation phase. Now, we could expand this flow chart to say, well, if we're going to value these things, and we go back to Greg's comment, we could actually estimate taxes or charges associated with the emissions, and then close the loop in the flow chart, where the taxes then influence economic activity, which then results in different levels of emissions, and so on and so on. And we've done that kind of modeling. In what I'm looking at today, since I'm stopping, if you will, at valuation and reporting these damage costs relative to various measures of value, I'm stopping here, but you could imagine cases in which this loop closes and this information is used to influence the price of products, consumer demand, and production processes.
So, question at this point.
Mhm.
Normally, GDP is done at marginal values of everything, so like market price and so on. And so the inflation fits into that nicely. This is your valuation of damages marginal, or is it more like healthy people are not damaged very much, unhealthy people are damaged very much, and there's a point in the middle that's the marginal point? So you stick to the marginal point or integral over all people?
Yeah, it's a great question. So what I do is I run this model once with all of the reported emissions in the economy to get a baseline of damages, which tends to be somewhere in the neighborhood, as I say, currently of about 5% of GDP. To get a marginal value, what I do is I literally add 1 ton of a pollutant in a simulation to a particular source and then run the model again and compute the delta. So it's not an elegant true derivative, but from the perspective of a source that might emit, 100,000 tons of sulfur dioxide in a year, when I add a ton, I track its impact across exposed populations. It's a pretty good brute force approximation of a margin.
No, it's a numerical derivative. That actually makes a lot of sense. Thank you.
Yeah. Part of what's, I'm sure there's some CS folks in the audience. Part of what's been really interesting, the first version of this model I started working on in 2002, completed it in 2004. We started publishing with it in 2006. That process of iterating over tens of thousands of sources and multiple pollutants with a high degree of spatial detail took a long time, 20 years ago. And now you'll see we've changed the resolution of the model, so it's much more spatially resolved. So we're actually doing this over many, many more both dimensions and observations, and we still do it much more quickly. So the extent to which the improvements in computing power have facilitated meaningful refinements in not only, in some sense, accuracy and resolution, but methodology has been really fun to participate in and to help guide PhD students as they work through those improvements.
Yeah, makes a lot of sense. Thank you.
You bet. So emissions data come from official sources, if you will, in the US, from the National Emissions Inventory, which is published by the US EPA. This is an important point when we think about the metrics that are used in the financial services industry to measure firm performance, because often what those metrics use are firm self-reported emissions, which in some cases may be fine, in other cases may be really rough estimates. And in these cases, many of these emissions are actually measured. So these are really accurate depictions of that step between economic activity and production and the residuals that are produced associated with it. So we track 5 economically significant air pollutants. These are particulate matter, PM2.5, sulfur dioxide, nitrogen oxides, a class of volatile organic compounds, and ammonia. We also track in a parallel modeling exercise, I'll talk very briefly about the 3 primary greenhouse gases, CO2, methane, and nitrous oxide. That tells us, or the conclusion from this is that we are tracking 8 pollutants, whereas many of the metrics that are tracking pollution impacts and firms' environmental performance are just focusing on CO2. So this is really a much more complete picture of how firms and industries and sectors are performing. And of course, as you'll see, I'm going to show you a bunch of maps in a minute. We know where the sources are. We know where the emissions occur. When we're talking about mobile sources like cars and trucks, we have estimates by county and by tract. Of course, there's noise and movement within counties. Anybody that lives in a city knows that's true. So we're approximating the emission location by centroid or by county centroid or tract centroid in that case. So for air pollution, we use what's called an air quality model. This is a very, very simple schematic just to provide insights into the rough sense of how these models work. The little cylinder on the left side of this figure is intended to mimic a smokestack, right? And we know from the emission inventories its height, its diameter, the temperature of the flue gas exit velocity, all of which go into the numerical calculations that dictate the plume shape and the plume rise. And then we use environmental and meteorological data to tell us where that pollution goes once it's emitted. The key assumption here is that the dispersion is governed by a 2-dimensional Gaussian distribution. You can see in the horizontal plane and the vertical plane, there are 2 little bell curves in here. This model is called a Gaussian plume model. At its core, in the most basic sense, these have been used for a long time to emulate air pollution emissions, also water pollution in water columns with rivers and lakes. The direction of the flow of the pollutant once it's emitted is, of course, governed by meteorology. The important thing to say here is much of what I'll present are annual averages. We do have daily modeling capabilities. If we wanted to look at, say, what happens when a particular power plant emits in a particular atmospheric regime, we can model that. But if we're doing this for tracking performance of companies and industries and sectors and economies over time, an annual snapshot is really all that we need to make those conclusions. And so what that means is, and I'll show this in a map, when you think about what this figure is showing, the wind direction arrow is it's singular. It's just blowing from the west. What, in fact, we observe in the meteorological data is a probability distribution. And so just to fix ideas, if it were equally likely that the wind blew from any compass direction, what you would get in terms of a map is just concentric circles, where you'd have decay of the concentration coming from a source with distance, but it wouldn't depend on direction. What we get empirically are basically ellipses, given prevailing wind directions, and all that is reflected in the modeling that we do. So this is a map of a recent year's. Sorry, go ahead, Greg.
It's perhaps a minor detail, but a lot of pollution is depends on the time of day. So manure would be a daytime thing because that's when it heats up, and industry will also presumably be daytime. Do you capture that?
So we have the capacity to capture that, but what we use in these annual exercises are average temperatures, average atmospheric pressures and wind directions. Colleagues of mine have looked at seasonality in particular, and that can be important. We have a summer ozone season for a very good reason. When it's warmer, you get more production of that pollutant. So those are important things. When I jump to what are the damage endpoints that we track, and I start to focus on premature mortality as our big one, it turns out from the epidemiological literature that it's the annual average exposure that drives much of that impact. So it's not, was it a particularly polluted day yesterday that drives mortality impacts. Rather, it's the cumulative exposure over the course of a year and over the course of multiple years that drives these really pretty big changes in baseline mortality risks. And those tend to be concentrated in populations that are already at risk. So if you get highly polluted years, we're going to start seeing enhanced mortality risk among senior citizens, amongst folks with pre-existing conditions. You do definitely see a mortality signature for the very, very old and the very, very sick for acute episodes like wildfires.
Right.
But again, the bulk of what the epidemiological literature tells us is that it's the annual stuff that matters, which is why in baseline, we take the annual average approach.
Okay, so then probably the only correction to make is if prevailing winds are different day and night versus summer, winter, that might be it sounds like a minor adjustment to your calculations.
No, I mean, I think I don't know that it's minor in certain cases. So I could imagine a case where if we're talking about a population that's particularly susceptible to ozone exposure, and we have a particular set of wind directions that are more common in summer, and we really only have ozone formation in the summer, then taking an annual average approach could result in a significant downward bias in the damage estimates, for instance. So I think it's a well-motivated and reasonable set of questions. What the research has shown, though, is that those daily and acute effects tend to be about 10% of what the annual effects are.
Right.
And so if we're making a mistake, it's probably in the range of 5 to 10% on top of that. So still likely probably small.
Cool. Thank you.
Sure. So this map is showing us the estimates of annual average fine particulate matter in every county in the US, produced by the AP4 model that I should say is available for free for download on my faculty website at CMU. There's a user manual, all that stuff. I've got 15,000 registered users. So it's a nice resource for academics. Private sector folks use it and regulators use it as well. If I had shown you this map from 15 years ago, you wouldn't see what you're seeing on the West Coast, because wildfires were not a contributor like they are today, and in this case in 2017, which was a really, really bad wildfire year. You would have seen a much more stark, basically 100-degree longitude line with pollution higher in the east and lower in the west. Because of all the fossil fuels in the power grid and the manufacturing sector in the eastern US. But that's really changed in recent years with the retirement of coal, cleaning up of heavy manufacturing and the use of electricity, and then the wildfires. What I want to show you next is just a very quick performance evaluation and a set of training exercises that we always do with the model before we use it for peer-reviewed publications or before we release it for regulatory use or for use by private sector folks. And all we're doing here is taking actual on-the-ground monitoring values. So EPA, not surprisingly, has air pollution monitors scattered throughout the US where they monitor pollution levels for regulatory purposes. We scrape that data, we assess the performance of the model, and we have 3 training rounds that we use to get the really good alignment that you see on these box and whisker plots, so that we're confident that in baseline the model is taking the emissions data and it's replicating an observed surface of air pollution that the monitors tell us is evident across the country. And the various compounds here are just constituent parts of different types of pollution that we track. So this is an interesting set of maps. The top graph is showing you the contribution of PM 2.5 from wildfires. I should say from wildland fires. The western stuff makes sense. Those are the big forest fires. The hotspot in the south central US are from prescribed burns, which are intentionally set to manage fire risk, but you're still producing smoke. And so we have a paper that looks at the impact of some of those. And all of the other emission sources in the economy, not wildfires or prescribed burns, are shown in the bottom screen. So that bottom panel, panel B, is what air pollution looked like 15 years ago in the US, because there were wildfires, but they were not on the scale that they are now. And so that this gives us a sort of a sense of the regime change in terms of the sources of air pollution in the US. That elevated PM concentration in the eastern US, as I said in the bottom, is really from residual coal that's still making power, natural gas, and manufacturing. And then the last piece is just generally more people. So there's more driving, more commercial activity and sources of emissions.
So
this
one
graph,
question,
yep.
Curious. So prescribed burns, there's obviously good motivation for it, but an alternative way of doing the same thing is to collect that same material for bioeconomy processing. And it seems like this kind of data set can give you the additional value of replacing prescribed burns with this management practice in addition to selling the stuff. Is that fair?
It is. Especially, I'm just jotting down a note, especially since we are looking for low or zero carbon sources of energy that we can use in industry or in electric power generation. So I think there's potentially 2 or 3 benefits rolled into that.
So there it's taking the stuff, burning it, but maybe then scrubbing the smokestack.
Yeah, the way that is at least proposed to be done, it's starting to be done in Northern Europe. It's called BECCS. It's bioenergy with carbon capture and sequestration, right? So you harvest what you don't want to burn in an uncontrolled environment. That's your point. You bring it to a facility, you burn it, but you capture the carbon as it's leaving the stack, and you sequester that underground. Yeah,
makes a lot of sense.
It's amazing when we, I don't have these results here, but when we compared the true wildfires with the prescribed burns, the air pollution damages were basically equal. It's not because the emissions from the prescribed burns were on the same level as the wildfires. It's that they were conducted in areas that were much closer to big population centers, which is why you're doing the prescribed burns in the first place.
Right.
Yeah. Sense. So it's sort of a, I'm sympathetic to the regulator who wants to manage the fire risks, but it's also important that they think about this other class of risks.
Right.
Okay. These are showing you wildfires again in the top, and then the bottom map is showing you ambient concentrations from all of the fossil fuel fired power plants. And this, I just can't emphasize enough how big of a change this is from when I started doing this work, and half of our power came from burning coal compared to under 20% today. So this is a deeper dive on how the model works. The difference between the two panels is not really that important. It's a technical difference between whether spatial interpolation and smoothing is used. But if we look at the right-hand set of maps, what it's showing you is the change in concentration from an additional emissions at the blue diamond, at a source location. And it's showing you the importance of prevailing winds and how the marginal contribution, the delta in concentration, decays as you get farther from a source. And so the thing to bear in mind is that that calculation is actually done for many, many thousands of sources, and for each of the 5 air pollutants. And those are then integrated together to build the baseline concentration maps that we were just looking at, right? So all of these modeling exercises are done in tandem to build the atmospheric conditions to upon which the chemistry calculations are made, from which the total ambient concentration calculations are made that give us the map. This is just sort of opening up the hood and saying, how does this model look spatially when you run it for one source? It looks like this. This is also important because when we do the marginal calculation that we were talking about a few moments ago, where I just add a ton on top of the baseline, it's these results that are, it's this capacity of the model that's critical, right? Because we're then going to ask who's exposed to that delta, and then what are the impacts from those exposures from that delta? And then we total that up, and that's our marginal damage that gets multiplied by our emission total. Okay, so exposure and impacts. There are a whole host of impacts of air pollution, and they're listed here. In the interest of time, I just want to say that about 80 to 95%, depending on how you model it, is coming from premature mortalities. And I've published in this space for years. I used to report all these damages and add them up, and I would get criticized for double counting, in particular, acute short-term illnesses that may culminate in a mortality. If you count both of those, there's a potential that you're actually counting the same event. So if you value an ER visit for asthma and that person ends up dying, some part of that mortality event is actually likely represented in the value for the ER visit for the damage associated with the ER visit for asthma. So what you'll see from here on out is just mortality. And these are still appreciable numbers relative to conventional measures of economic output. What I do is rely on epidemiological dose response functions. There's been a long literature in public health and now in applied microeconomics that links exposure to pollution to adverse health effects. I'm just a consumer of those. I use those functions in this model. The final step then is valuation. This does two things. It allows us to build the GED measure that gets deducted from GDP. We've talked about that a lot. But also note that if we're talking about a pollutant with disparate impacts across sectors like agriculture, man-made capital, and human health, you can't add up bushels of wheat, tons of iron, and lives lost, but you can if you monetize. And so by converting those to a common unit of account, then we can build a more comprehensive measure of pollution costs than if we were just looking at one particular endpoint. And so that's another motivation for monetization. When we think about monetization in the context of mortality risk, it may sound crazy, but we consumers actually value mortality risk reduction all the time. We do it with consumer products like clean water, fire extinguishers, bike helmets. We also do it in the workplace. And there's decades worth of evidence that when you standardize by industry and by sector, more dangerous jobs, that is with higher reported on-the-job fatality risks, command a wage premium. And they should. We should have to compensate workers for risks that they take to their health by working in particular contexts. So two approaches to estimating what's called the value of a statistical life. It's this marginal trade-off between income and mortality risk. One uses wage data. The other uses what are called highly structured preference elicitation instruments like surveys to ask people directly. All right, so I'm going to just keep moving. The routine or algorithm that I mentioned earlier, Greg, is outlined here. That is, run the model to baseline, add a ton of one pollutant to one facility, run the model again, total up the delta damage. That's the damage per ton of a pollutant from a facility, repeated over thousands and thousands of sources and over multiple pollutants. And we get the damages per ton listed in this table, shown on this map for primary PM 2.5, for sulfur dioxide, for nitrogen oxides, and on and on. And then the final point is to say when we value greenhouse gases, we're using what's called the social cost of carbon. It's a whole other set of issues associated with estimating that dollar per ton impact for CO2 equivalents. I'm not going to get into those here in the interest of time. I'm using values for the social cost of carbon that come from a meta-analysis done by really, really good economists and the US federal government. Okay, all right. So results. This is a figure showing GDP growth, so indexed real GDP, the solid line from the late 1950s to basically today. And the vertical bars are recessions, official recessions. And so the conclusion for GDP is that it's basically tripled since the late 50s in real terms, 300 relative to 100. The dashed downward sloping line is air pollution damage. And you can see that despite all that economic growth, our real measures of air pollution damage have fallen. The economy's gotten cleaner. And that means when we look at our adjusted measure, EVA, it's actually increased by more than GDP. This result is just telling you what that bar chart very early in my slides told you. When you deduct off pollution damage and it's falling relative to GDP, your adjusted measure is growing more rapidly. We've mismeasured growth, and we've mismeasured growth downwards. This is taken from an article in Science. It's showing you the same thing. It's just looking at a more modern series of years. It's just telling us that EVA in the US growth has outstripped GDP over about a decade, in this case, leading up to the financial crisis. This next slide is loading, I think. There we go. It's showing you gross state product and the share of air pollution damage relative to gross state product. And really the point here is to say, not surprisingly, this pollution burden is heterogeneously distributed across states. In the 90s, there was a bunch of coal-fired power generation. The Rust Belt was still a thing, and you see very high levels of pollution damage relative to gross state output In West Virginia, in the Rust Belt, in North Dakota, and Wyoming, there's a bunch of agriculture and fossil fuel extraction in those sites. When we look 10 years later, the picture changed quite a bit. And we have not replicated this for the modern era, but I would anticipate continued declines, especially in the Rust Belt, as more coal-fired power has retired. So this is a paper that looks at the pollution damage intensity by sector, and you can see vast differences between manufacturing at just 1% of value added to utilities at 35% of value added. If we drill down even more and look at damages per value added by industry, I was mentioning this earlier, if you look at the fourth entry, coal-fired power generation, damages in the early 2000s were 2 times value added. So when I talked about NRG earlier, and NRG owns a bunch of coal assets, we weren't surprised to see the results for NRG, given this research that came from some years earlier that showed us when you just look at coal-fired power generation generally, the pollution damage share is disproportionate to value produced by those companies. This is just showing the utility sector generally over about a 10-year period. It's emphasizing this difference in apparent growth. Utilities are generally perceived to be very low growth firms. So the annual value added growth in the sector over this period is very, very modest, under 0.5%. But when you build in the reduction in damages, the apparent growth is actually really, really rapid. It's nearly 20%. And that's because from 2010 to 2020, this sector abated a whole bunch of local air pollutants and greenhouse gases, which when properly priced, really radically changed the net value in the companies in this sector. Okay, so if we drill down to the firm level, these are roughly 300 companies in the S&P 500 that we could find facilities that they owned in the official emissions inventories and then model those impacts out. The pie charts here are showing you, the top pie charts are showing you the distribution of damages, pollution costs, across the sectors. And the take-home message here for damages is over 3/4 of the damages from all these companies come from utilities. In contrast, when you look at the bottom pie charts, these are value of companies. If you look at utilities, look for the blue sliver. These companies are contributing over 3/4 of the pollution cost, but they're contributing something like 5% of market cap to the total S&P, the sample of S&P companies that we track. So that should tell the investor, if you're really interested in environmental performance, you have to be very careful about investing in utilities, in energy companies, and some of these other more pollution intensive sectors, because there's at least some evidence here that they are contributing far more to social cost than they are to aggregate value. Now, lest we paint with too broad a brush, we find that within each of these sectors of the S&P 500, there's actually vast heterogeneity in this share that the companies contribute to damages and to sector value. So if we look at the top pair of pie charts, now we're looking at the materials sector. We blow that up and we say, okay, among all of the damages that those companies cause in that sector, who are the main contributors? And you can see it's Eastman Chemical, and then it's two paper manufacturers. If we go down and we look, we find that combined, those 3 companies contribute, I don't know, what is that, 10%, 12% of total market cap. They're contributing over 1/2 of the total social cost coming from the companies in this sector. And we find this pattern repeats over the different industries and sectors in the S&P 500. There's actually a really interesting investment lesson or guidance that comes out of this work, and that is, it appears actually that you can diversify a portfolio into some of the sectors that traditional metrics would say don't invest in, because what's actually evident in the data when you actually apply the science-based models to track these impacts is that it's really just a small number of companies within each sector that are contributing the large share of damages. And you can invest in other materials and industrials and energy firms as long as you avoid some of these that are particularly pollution intensive. This is showing you a firm level depiction of what we've talked about now for an hour, which is what are the damages relative to value? And if we look up at the top, there's NRG, and it's got damages that are roughly 75% larger than its market cap. And you can see there's a small number of companies across all these firms for which pollution damages actually contribute a large share or are large relative to the value of the firm. Evergy, Ameren, AES, First Energy, AEP, and Energy, and NRG, I should say. It's not until you get further down that you even get into energy companies and materials manufacturers. So this is really concentrated in some of the utilities that are at that time relying on coal. Okay, so then the final thing I want to chat about just very, very quickly, this may be interesting for those of you who are interested in measuring impacts in supply chains. This is doing the same thing. It's measuring impacts of pollution, it's costing them, and it's expressing those relative to GDP. So GED over GDP is the same metric we've been talking about, but now it bins countries by income status. These are World Bank income groups. And the thing I want to highlight on this screen is there's been a bunch of cleaning up in Western Europe and in North America, developed economies. GED relative to GDP fell from about 10% to about 7% over the last 20 years. That's progress. However, if you look at the top right-hand panel, which includes China, it tells us that all we did is move pollution intensity from one set of economies to another, right? Those upper middle income countries went from 7.5% to 10%. High income countries went from 10% to 7.5%. That's trade. We can drill down into the G8. There's two basic patterns. Western Europe, declining pollution intensity. China and India, increasing pollution intensity. Not surprising, but quantified. These are global growth rates. And you can see the tipping point here, the big change was the Great Recession when trade flows started to change and much more global output was produced in India and China, which had higher pollution intensity, which mitigated the difference between EVA growth and GDP growth because global output started to become more pollution intensive when we shifted manufacturing into dirtier economies like India and China. And then these are the growth rate differentials, and the main story here is just that when we look at China and when we look at India, this calculation reduces apparent growth. Now, not enough to make a meaningful dent in 15% annual growth in China in the early 2000s, but nonetheless a negative differential. Okay, so those are my concluding thoughts. Thank you very much for the opportunity to present. If there's time, I'm happy to entertain questions.
Well, first of all, thank you very much.
My pleasure.
The one big question that I'd love to learn more about is you focused on short-term damage pollutions, whereas climate change things is most of the damages are farther in the future and potentially catastrophic, and importantly, non-linear, where there's like some runaway effects that may happen with some probability.
Yeah.
How can you model that? And so how are we doing on the intensity of the long-term damages?
Yeah, so it's a really important question. So most of what I presented in terms of results, not all, but most included both greenhouse gases and local air pollutants. So the way we value emissions for greenhouse gases is with the social cost of carbon, which is the present value of the stream of damages that a ton of emissions causes. Right? So the long run piece is embedded in that present value calculation. However, the runaway scenario, the nonlinear hockey stick scenario where damages are abruptly much higher than we thought in 2050, the only way that we approximate that in this modeling work is to say, okay, when someone is calculating the social cost of carbon, they pull from a distribution created with Monte Carlo simulations the 95th percentile realization of that per ton damage, which might be 2x or 3x the median. We use those, we generate estimates. They don't do a lot in terms of changing the story. However, I'm skeptical that that 95th percentile from a highly parameterized distribution and set of calculations for future damages actually captures what that catastrophic scenario would look like. My gut tells me it may be much more. And in light of that, we should be valuing the tonnage in those scenarios much, much higher, maybe 10x of where the mean values that I'm using in these default scenarios lie.
So then one extension might be there's social cost of carbon that are $185 and they have their own ranges that can go into thousands. How much would changing that the SEC change your conclusions about the cleanups?
Yeah, so in this on the screen that we're looking at, so the US, one of the figures in the appendix of this paper decomposes this into PM 2.5 and CO2, so air pollution and CO2. The CO2 line would probably start to take this downward trend and flatten it considerably, right? Because it's not until the Great Recession in the US that emissions actually started to fall in total. So you would see flattening. France, probably not so much. They don't emit a lot of carbon. There's a lot of nuclear in their grid. UK and Germany is probably very similar to the US. This cleaning up pattern, if we were valuing at the SEC at $1,000 per ton, these lines would flatten and China and India would steepen in the wrong way.
Right. And then how would you incorporate cleanup efforts? So CO2 would be growing forests, particulate might be, I don't know, scrubbers.
Yeah. So if we're talking about observations, so in the recent past, how decarbonization has happened, that's in the data. And so it's in there whether we're valuing with $1,000 a ton or $50 a ton.
Okay, right.
If we're looking forward and we're modeling scenarios where there's a lot of cleanup, that's going to pull down the damage per ton, because what those scenarios, lots of cleanup moving forward, are doing is lowering the concentration of carbon dioxide in the atmosphere and making current tons emitted less harmful because they're persisting in an atmosphere that has less carbon in it.
Right.
Yeah.
Makes sense. And maybe last one is, so actually looking into the forward and the future. So your integrated model looks at the attribution of pollution to damages and so on. But if you want to look forward, you want to start incorporating what, like, the IM3 model, those integrated assessment models that say, like, here's the sectoral dynamics, and now you start modifying their market model with the damages, and like, how might that work out to start driving the future industries differently when you do account for these costs?
So that's great. We have some research at Carnegie Mellon that uses, they're fairly aggregated in the sense that they're not at the firm or facility level, what are called energy system models that run, you can run them really to 2050 to 2070. And we've run experiments where we have taxes for local air pollution and carbon taxes in place. And what the energy system model does is finds the least cost means to employ technology as fleet turnover occurs to meet exogenous demand for various services. Energy is one, transport's another, et cetera. So when you think about the future, it really depends how you communicate the information in the damage calculations to economic agents. And the most straightforward way to do that from a modeling point of view is to price it using taxes that then get forcibly internalized by firms, and you see differences in investment and differences in production processes as a function of those policy instruments. That's the way it's typically done. I mean, there's certainly ways you could think about companies trying to decarbonize or trying to clean up autonomously, that is without a policy signal.
Mhm.
But the sort of endogenous modeling tools and equilibrium modeling tools typically require a policy signal in order to affect or cause, for lack of a better way to put it, industrial composition and technological change.
Right, right. There's an extra cost to a given action. Yeah, makes
Exactly.
sense. All right, cool. Yeah, thank you very much. This was all very valuable and fascinating.
Thank you. Be well.